analog electronics. There's two sides to the electrical house. One side is analog electronics, the other side is digital electronics. DC is part of analog, AC is part of analog, and then there will be one more course you would take, and that will be, well, in some places they call it solid state, here they call it electronics. So we have 3 analog courses, so you're 1/3 of your way through that. Now, some of you, depending on your major, if you're electromechanical, I don't know, some of the majors do not, and his screen is not showing for anyone else. No, I guess nobody else can see Nathan. I wonder how come you guys can't see everyone's screen.
I can't even see your, like, the whiteboard or anything.
Oh, you know why? Because I have the camera off. Let me turn that on. Can you see it now?
Yeah, that's good.
I got so excited about Nathan's picture of the chickens, I just forgot to turn this on. So thank you for reminding me. But what I was saying was, if you think about electronics, and this is what you guys are in, there's 2 sides of the electrical house. There's the analog side, and there's the digital side. Analog means the signals are continuous. Digital means the signals are broken up, and they're represented in what we call bits, or they're represented using what we call 2-state electronics. And so with DC, there's AC, and then there's electronics. And those are the 3 analog courses that we have here at Cincinnati State. And so now you're 1/3 of the way through once you finish this course. And I did talk to at least one other student. I mentioned, you guys, since it's early in your degree program, you need to think about a second major. At Cincinnati State, we get 2 degrees, not 1. I had a double major at Xavier. My major was physics and philosophy. I got 1 degree in physics, and they just stamped on my records, my grades, my student record, that I also completed the degree requirements for a degree in philosophy. I didn't get a second degree. At Cincinnati State, they're kind of unique in that they get 2 degrees if you have a double major. If you don't have a double major, you get double degrees, and that can make you very, 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 very marketable if you choose the right thing. So I did have one student approach me to ask questions about that. Keep that in mind, because in some cases, a requirement in one degree is an elective in another degree. So if you line your ducks up, or in this case chickens, I guess, the right way, you can get 2 degrees and just have to do a couple more classes. So I don't know if I'll see you guys anymore, because I'm teaching AC, but I'm not teaching it next semester. I'm not teaching it until fall, so I won't see you. So if you have any questions concerning that, if you're taking AC over the summer, and you have questions in AC, feel free to keep in contact with me. Best way is to text me. You can email me, but keep in contact, and I'll be happy to assist you in any way I can. So I want to finish our final lecture, and I was looking on Blackboard. For this class, this is 51 lectures. There's 51 lectures. I think on YouTube, we have so far, altogether between Cincinnati State and UC, 126 videos, and I haven't even put all the videos up. So if I add the 51 from your class, and then the ones I didn't put up, they're probably well over, I'm guessing, probably 200 to 250 videos. Now, the reason I'm saying that is I'm going to leave that stuff up on YouTube. When we go back face-to-face in fall, I'm not going to delete any of that stuff. It'll be deleted from Blackboard, but it'll be up on YouTube. So if you go on for your bachelor's, if you need to review stuff, all that stuff will be available to you. I mean, I'm not going to make any more new videos, but there's a ton of stuff up there. And on the UC stuff, I actually go into some of the digital. It's not really a digital class, it's a PLC class. But in the beginning of that, we talk about some digital concepts. So, explore that website. I don't know whether it's Cincinnati State Tutorials. I think I had one of my students build it for me, so I don't know what he called it. But you guys have the link to it. So if there's anything I can do, just keep in contact with me. I really enjoyed this class. I don't know. In the beginning, when we went through virtual, because I'm a face-to-face person, I didn't think I could teach like this, and now I've become accustomed to it. I didn't like one summer we tried to do online labs, and I told them that would be a catastrophe, and it was. So they quickly went to in-person labs. So I really enjoyed having you guys come over. for the once a week for the lab and do the lab, and then I think it's convenient because you can always go back and rewatch the class. So there's a lot of advantages to doing this. And I think I mentioned to John and a couple other people that even after this COVID is over, I don't think we'll ever, when I say we, I don't mean just Cincinnati State, but society as a general, we've learned that there's things that we can do that we didn't know we can do. I didn't know I can teach like this. And there's companies that would have never before COVID allowed their workers to go home and work. But I think a lot of companies are saving money. They don't have to heat buildings up. They don't have to build parking garages. They don't have to do any of that stuff because now they learn that people can do productive work from home. And so I'm going to keep some of this alive and going, but I don't know. We'll see what happens. So the final lecture of the semester, the final topic is inductors and inductance. Now, what I want you to do is to think of kind of capacitors and inductors that kind of go together. I don't mean they work together, but both of those devices are what we call energy storage devices. Both capacitors and inductors store energy. They have physical differences. You already know that a capacitor is basically two conductors separated by an insulator that they call a dielectric. We'll talk about today what an inductor is, but the main thing other than the physical differences is where the two devices store energy. Capacitors store energy in the electric field that exists between the plates when you charge it up. When you charge up a capacitor, you'll have one plate being charged positively and the other plate will hold negative charge. So these are my two plates. When I have a fully charged capacitor, I'll have positive charge on one plate. I'll have negative charge on the other plate. Well, you already know from our discussion during week 2 of the course, what is voltage? Voltage is the separation of charge. And if I charge up the two plates of the capacitor, since there's an insulator in between, there's no way for the positive and negative to get together. So I have charge that's been separated. I have a voltage. And anytime you have separated charge, between that area of separation, you have a field called the electric field, and that electric field stores energy. We mentioned fields back, I don't know if you remember during week 2, we said fields can carry energy and fields can carry forces. So here's a situation where energy is stored in the electric field between the plates of a fully charged capacitor. Inductors are a little different. First of all, what is an inductor? Well, all an inductor is a piece of wire. All an inductor is a piece of wire. And if I share the document with you, and I put this up on Blackboard, so I don't know if you had a chance to look at it yet, but if you looked at it, then if you didn't look at it, then I'll share it with you. If you did look at it, that's fine. If you look at my definition and the equation, then you will see the definition here that I have written for inductance, and then you will see the equation. We had an equation for the physical construction of a capacitor. Well, here's an equation for the physical construction of a inductor. So, what is inductance? Inductance is the ability of a conductor to produce and induce voltage when the current varies. Let me read that a second time. Inductance is the ability of a conductor to produce and induce voltage when the current varies. Now compare that to our definition of capacitance. What is capacitance? Capacitance is a device's ability to store or hold charge. Capacitance is a device's or material's ability to store or hold charge, whereas inductance is the ability of a conductor to produce and induce voltage when current varies. Well, what the heck does that mean? We'll talk about that. We'll talk about that in just a second. But what I want to do is focus on the equation, the physical equation for inductance. And just like we had one for capacitance, I gave you one for conductance, for inductance, and the subscripts below, or the definitions below, are a little hard to read, but I'll read them for you. You have L, We use a capital C to represent capacitance. We use a capital L to represent inductance. So L is for inductance. The more inductance a conductor has, the greater the ability to induce a voltage across itself. And we'll talk about that ability to do that in just a few minutes. But that inductance is measured in what we call henries. Henries, the symbol for Henry is a capital H. So in this equation, the L is for inductance. Now this second symbol is the Greek letter mu. So right here, this is a constant. Now you know we had a dielectric constant when we talked about capacitors. Well, here with inductors, we have what we call the relative permeability of the core material. Sometimes when you have a conductor, I keep saying conductor, I mean inductor. When you have an inductor, you'll have a core in that inductor, and I want to show you on the board when I switch off from this in just a second what that looks like, what that is. So typically when we have a piece of wire, we're going to use it as an inductor. We do not use the wire in a straight. We don't keep it straight. We coil it. We loop it in the coils. So N in this equation, in this formula, is the number of turns on the coil. And then A is the area of each turn in square meters. And L is the length of the coil in meters. And so there's our physical definition for inductors. And I want to show you on the board. I wrote the equation out on the board, but I want to show you kind of actually what it looks like. Now, in the equation I just read, here's our L, here's our mu sub R, it's N. It looks kind of weird because the way it's written on the paper, there's an N and there's a 2 there. It's because I couldn't get, when I wrote the formula out, I couldn't get it as a superscript. So it's really N squared. It looks like on the equation N times 2, but it's really N to the second power. So you want to make yourself a note there in case you look back later on and say, what the heck is this N2? Well, it's really N to the second power times A. Now let me draw what this looks like. What you'll have is, oftentimes you'll have a metal core or some kind of core, and then you'll wrap wire around it. So the actual inductor is just a coil wrapped around the core. And we bring the wires out like this. So this is called a core. And this area, if you were to kind of point this towards the camera, you're looking at the area of the core. If there's no core, if we just had the coil, and you look at the side of the coil, and the area would be the area where the core would be if you had a core. So that's the A you would put into there. Now, usually we use a capital L for length, but since we already use a capital L for inductance, they use a lowercase l for length. So the length would be the actual length of the coil. So that lowercase l is the length of the coil from there to there. And this K right here, I don't show K on it out, but K is this number. And what I like to do is when I have a constant, I mean, I did the same thing with the capacitor, if you think about it. There was a constant, but I hid it in that K. It was K sub epsilon times some constant. Well, there's a constant that you multiply this by, that's 1.26 times 10 to the minus 6. Rather than write that to make the equation look more complicated, I decided to just call that K. K equals this, so I just stuck the K up there. And the unit is, of course, in henries. So the point of this is there's nothing you have to remember. We could do if we wanted to exactly the same thing we did with capacitors. We could compare the capacitance to the number of turns. The inductance to the number of turns. We can compare the inductance of an inductor to the area. We can compare it to the length of the coil. We can make the same comparison. Now you might wonder to yourself, well, okay, we got this new device we're talking about. We waited to the last day of the semester to talk about it, and we spent a whole bunch of time talking about capacitors, and we only spent a little bit of time talking about inductors. Doesn't mean inductors are not important, but I did that on purpose. The reason I spent the majority of the time talking about capacitors is when you're using these energy storage devices, there's times when there's times where you have to use a capacitor. And then there's other times where you have to use an inductor. But often you can use either or. You can use a capacitor or inductor. It just depends on what you're doing. When engineers are designing devices, when they can do it, they try to get away from using inductors. They try not to use inductors. Now, I want to explain why in just a second. When I talk about, I want to go back to that definition for inductance, and then I want to explain why engineers try not to use them when they can. So let's go back to this definition that I have in the box on your topic sheet. It says inductance is the ability of a conductor to produce an induced voltage when the current varies. What does this term mean right here, induced voltage? And where have you heard that term before? What does it mean to induce a voltage? How do you induce voltage? There's only one way to do it. How do you induce voltage? Well, I'll tell you, let me give you a hint. I will remind you where you saw an experiment of voltage being induced. Remember the video I showed you where there was a gentleman who had a magnet, he had a coil of wire, and he had a meter, and he hooked the coil up to the meter, and he moved the magnet in and out of the coil. Because somebody explained to me what was happening in that video. What was he doing?
Creating voltage.
He was creating voltage, but the correct term is inducing voltage. An induced voltage is a voltage produced not by a battery. We know batteries separate charge. The other way to make a voltage is what we showed you using whose law? Faraday's law. So when you create voltage, I believe that was Tim, when you create voltage, as Tim said, when you do it not electrochemically like a battery, but electromagnetically using magnetism and coils, then we call that voltage an induced voltage. So am I saying that inductors produce voltage using Faraday's law? Yeah, that's exactly what I'm saying. If I have a piece of wire and I have now here's what's different. Here's what could be different. With the induced voltage in the video, the guy had a coil. Now, remember what I said an inductor is just a coil. So even though in the video he called the coil, that was an inductor. And he showed you that, I erased the equation, but we had L, the inductance, and we had N squared over here. They were both in the numerator. So you can see in that equation that I just erased that the inductance, the ability of the conductor to generate an induced voltage across itself, is directly related to the square of the number of turns. So you saw in the video that when he went from a coil of 1 turn to 10 turn to 100 turns, the induced voltage was greatly increased, because basically he was dealing with an inductor, and it obeys those relationships in that equation that I just talked about. So Faraday's law says that if I want to induce a voltage, I got to have a coil. Well, all that is an inductor. All an inductor is a coil. You got to have a magnetic field. And the last thing I got to have is motion. Motion between the coil and the magnetic field. And so there's 2 ways to do it. Well, there's actually 3, but we talked about 2 ways so far. I'm going to talk about the 3rd one today. The first way is the way the guy showed in the video. He had a coil of wire, he had a magnet, and he moved the magnet in and out like that to produce motion between the magnetic flux and the coil. Or he could have held the magnet stationary and moved the coil. Either way, there's got to be relative motion between this and this, between the coil or the inductor and the magnetic field. But there's another way to do it that I want to talk about, and this is the way inductors kind of work. If you have, well, let me just show you. When we talk about DC current, this is current, and this is time, and I want to make a graph of current over time. If I tell you this is DC, direct current, how should I make my graph? What should I draw? What does direct current look like in the graph?
Straight line.
A line.
So I should draw this. I should draw that. And it's usually okay to draw that, but this graph is actually not quite correct. There's something wrong with it, and I'll tell you where it's wrong. Right here, this is 0, so this right here would be t equals 0. What's wrong with that picture at t equals 0?
It should be sloping down.
It should be sloping down. Why? Because if you go by this graph, what you're saying is the second you turn the switch on, the current goes from 0 up to some steady state value in no time. Impossible. There's no way for the current to go from 0 to steady state in 0 time. Impossible. What happens is it takes time, T-I-M-E, for the current to build up to steady state, and then it stays, and you can, after that point, you can call it direct current if you want to, but all current, I don't care where it comes from, it's not really direct current because it takes time. It's going to go from 0 to steady state, and while it's doing that, while it's building up, it is not DC. It's only DC when it gets up here. Now the reason we can draw the graph like this, the reason I can get away with that is because this little bit right here, I drop the perpendicular down, this little, let's just call that delta t. That little piece of time right there is usually so tiny we can ignore it. But you can't ignore it if you're an inductor. Why? Because, well, remember when we studied electromagnetism? Or just remember when we studied magnetism in general? What produces magnetic fields? What's the cause of all magnetic fields?
Voltage.
Not voltage.
Current.
Current. The current. Riley's in the class. If you heard another voice, you can't hear him. He said the current. And somebody, I think that was that Nathan or Travis or somebody said current. Current is the cause of all magnetic fields. We talked about that. That was the essence of that quarter problem I gave you. We wanted to know why we had 2 quarters and we hold one and we let the other one roll around the other one without slipping. And I don't know if I ever gave you the answer to that, but only 3 people turned that in. That's a free quiz. Everybody else is going to get a 0 on it unless you get something to email or get it to me before I put my grades in. But the question was, if I have a quarter and I put my finger on it and I have a second quarter on top of it and I let the top one roll around the middle one without slipping while the middle one stays stationary, how many times would that one that you're moving, how many times would it rotate? And somebody correctly said 2. And my question was why? So I wanted you to try it and then write why you think the answer, well, why you think it is. And so, but the whole point where that came from is that electrons are both spinning and revolving around an atom, and that makes up a current. Now with electromagnetism, we look at wire and we look at current passing through that wire. And so current passes through a wire, so I have a magnetic field around the wire as long as current is passing through it. And you know from my discussion of electromagnetism that flux density is directly proportional to the current that produces it. The magnetic field is directly proportional to I. Well, look at this. If it's current, if any time current flows, there's a magnetic field produced, and the magnetic field is directly proportional to the current that produces it, what's going on from T0 to steady state right here? What's going on from T0 to steady state? What's happening there? How much current do I have at T0? None. How much current do I have here? A maximum amount. So while the current is building up, what's happening to the magnetic field? It's moving out.
Yeah.
Once we reach steady state, that magnetic field is static. And at that point, just from T0 to, let's just call this T1. At that point right there, between T0 and T1, can you see Faraday going on? Faraday says you have to have a coil. Well, you got it. That's what an inductor is, a coil. Faraday says you have to have a magnetic field. Well, you got that because you got current flowing. And if current is flowing through a wire, it's going to produce a magnetic field around that wire, around that coil. What we don't have is movement, but really we do. We're not, in this case, we're not moving the coil. In this case, we're not moving the magnet through the coil. The way we're moving the magnetic field is by varying the current. When that current starts out at 0, there's no magnetic field. When it builds up to the maximum amount, the magnetic field is moving out, and it builds up to the maximum amount of magnetic field. And during that time when it's building up, there's a voltage induced or produced across that wire, or in this case, across the coil if it's a coiled up inductor. So that's the third way to induce voltage. If I can just take a switch, or if I can take any way that I can vary current, I can produce voltage. I can get a coil to induce a voltage based on Faraday's law across itself. Now, I want you to think about that because we talked about some applications for capacitors, I think, or for electromagnetism. I think I gave you this with the rail gun, and we talked about motor action and generator. We talked about a lot of stuff, but there's a lot of things that we could talk about with inductors if you wanted to. Let me talk about this, and then I want you to think about how inductors work just a little bit more deeply. So what you have over here are, these are called differential equations. So I have a differential equation that says IC equals C times dV dt. Now IC is just the current flowing into a capacitor. And C is just what you think it is, it's capacitance. Now what might be new to some of you is this, dV dt. And I've talked about this before, but I want to mention it again. So dV dt, you can kind of think of that like changing V over changing T. If you know calculus, you probably would think about it this way. If you don't know calculus, you just know algebra, you would think about it this way. It's either way. Either way, I got a voltage over time. So my units are going to be, let's say I have, I change by 100 volts. And I make that change in 2 seconds. So what would my units be? Well, when I divide 100 by 2, I'm going to get 50. And my units are going to be volts per what? Per second. It'll be volts per second. So in every second, I change by 50 volts. So what this is a time rate of change of voltage. I don't care how you think about it. If you don't like that, then put this in its place. Either way, it's a time rate of change of voltage. Another way to say it is how quickly the voltage is changing. dV dt, or delta V delta T, represents mathematically how quickly the voltage is changing. And so what this says is that the current flowing into a capacitor is directly proportional to C. Let me write that down. Is directly proportional to C, but more importantly, it's also directly proportional not to the voltage, but to how fast the voltage is changing. So the quicker you change the voltage across the capacitor, the faster the current, the more current you're going to get going into that. Now I think on one of your capacitor homeworks, they want you to solve for dV dt. And I told you you can just write this, replace that with X, write that like IC equals C. Instead of writing that, just write that like X and solve that for X, and that would be your answer. But this is a differential equation that talks about how quickly the relationship between current flowing into a capacitor and how quickly the changes across the plate of the capacitor. Now today we're talking about inductors, so I want to show you the differential equation for inductors, and it's this one. What does this say? It says VL. L we use for inductor, so it doesn't mean V low. It means V across the inductor. It's equal to L, where L is the inductance. And then we have this was dV dt, this is di dt. So di dt, what is that? Well, this is the time rate of change of voltage, and di dt, which you can write as delta I over delta t if you don't like to write it this way. But this is the time rate of change of current. The time rate of change of current. Now, remember we said math is a language, and these equations actually give us information, they speak to us. Well, what is this saying? This right here is saying that the voltage across the inductor, the voltage across the coil, is directly proportional to L, but it's also directly proportional to not the current, but how quickly the current is changing. I want to say that a second time because I stuttered. The voltage across the coil that we're calling an inductor is directly proportional to L, but more importantly, it's directly proportional to how quickly the current is changing. The faster you change the current, the more voltage you can get across that inductor, across that coil. Now this has tons of applications, many applications. Here's one application. What ultimately causes your car wheels to move? I guess I'm asking kind of how does an engine work? What is the engine? Say it again, John.
Drivetrain.
Okay, the drivetrain. Okay. The drivetrain. So the drivetrain turns. What turns the drivetrain?
The engine. Yeah.
The engine. Well, what's in the engine that's moving?
Transmission.
Well, he says the transmission. The transmission is a moving part. But what's in the engine that's moving?
The pistons.
The piston. There's a cylinder. There's a cylinder. And inside that cylinder is a piston. So a piston is like a disc of metal that fits in there tightly, and it has a rod on it, and that rod is connected to the piston, and it can move up and down. Now, as it moves up, what happens is air is injected into here, air and fuel. What kind of fuel? Gas and alcohol mixed together usually. So we spray air and fuel in here, and then this thing comes up and compresses it. And then somebody lights a match. What happens when you light a match in a gasoline mixed with air situation? What happens?
There's an explosion.
There's an explosion, and that explosion quickly heats up the air, which expands and pushes the cylinder down. And it's a combination of those little explosions that causes this, basically ultimately causes your wheels to turn. Well, how do I get the ignition? Well, there's something right here called the spark plug. And that spark plug has to fire at the right time. It will ignite the air fuel mixture, causing a little explosion in the engine, and the expanding gases push the piston down. But here's the thing. In order for that spark plug, if you ever looked at a spark plug, it has an anode and a cathode. Now they're really, really close together. I'm gonna exaggerate it here. So on the spark plug, you get like the part you screw into the engine, and then there's like a little part right here. It's a metal part that comes up over like that, and the arc is right in between the metal part and the other part. That's actually a cathode and an anode. They're really, really thin. You can just get a couple of pieces of paper in between it. But what happens is when you apply a voltage here, you can get a little spark to go from the anode to the cathode or vice versa. And that little spark is what ignites the gas. But here's the problem the engineers were faced with when they made their first combustion engine. Is air an insulator? You think air is an insulator, a semiconductor, or a conductor? Just guess. Air.
Semiconductor.
You would think, but you would be wrong. Anybody else?
Conductor.
It's a very poor conductor, which means it's a very good insulator. Air is a pretty good insulator. It's a good insulator. And so it turns down that every insulator, you can turn any insulator into a conductor by producing enough voltage across it. Remember, voltage is like the force that make electrons move. I can push it against this wall all day long, ain't nothing gonna happen. But if I put a bulldozer against the wall, it's gonna fall over because the bulldozer can apply a way bigger force than I can. Well, voltage works the same way. If this is a piece of rubber and I put a battery circuit across it, nothing's gonna happen because that battery doesn't have enough electrical force, i.e. voltage, to cause current to flow through the insulator. If I get a big enough voltage, I can actually cause the current to flow through an insulator, and the voltage necessary or required for that is called the breakdown voltage of the insulator. Every insulator has a breakdown voltage. You go above the breakdown voltage of an insulator, then you cause that insulator to become a conductor. Well, it turns out that the breakdown voltage of air is a insulator. The breakdown voltage of air is, I believe it's 25,000 volts per inch. It's either 32,000 or 25,000. The point is, it's a huge number. I'm going to go with this number, but if I put this on YouTube and the YouTube people start commenting, it might be 32,000. I'm not thinking right now, but it's a lot. If we go with this number of 25,000, that means in order to get an arc across an inch is 2.54 centimeters if you don't know inches. In order to get an arc that big, between that distance, I need 25,000 volts or 32,000 volts. You ain't going to get that with a 12-volt car battery. Even if I put the anode and cathode really close together, like on a spark plug, it's still nowhere near enough voltage to get the current to flow through the air to arc. You're making artificial lightning. So the only way to do that is to make the voltage higher, make it bigger. Well, how do you make a 12-volt battery DC? How do you get more voltage out of that? You do this. They used to have it's done electronically now. They have electronic ignitions. But in the old days, they actually had a switch that will open and close. As your engine would turn, it will open and close the switch really, really fast. And when you open and close the switch really, really fast, you already know what happens to the current. If this is time and this is my current, when you open and close the switch, when you open the switch, or when you close the switch, it goes up. And when you close the switch, it comes down. And so from T0 up to this point right here, that little delta time, that little change in time right there, the current goes up really, really fast. That time is real small. That change in current or change in time is really, really quick. That change in current, change in time is what this is right here. So if you get that DIDT or that delta IDT to be really, really quick, then you can take a 12-volt battery and produce 100 volts. You can take a 12-volt battery and produce 1,000 volts. You can even take a 12-volt battery and produce 1,000,000 volts. It's really almost limitless. Because the voltage, we don't care about Ohm's law now. This ain't that. The voltage here with an inductor is the voltage is produced not by the current, but how quickly we change the current. When you open up the police stun gun, or the stun gun, and you look at it, there's a 9-volt battery on the inside of it. At least I had one. It was a 9-volt, a square transistor battery. Well, mine wasn't like the police stun gun. I had one. It was about the size of a pack of cigarettes. And then it had an electrode here, an electrode here. With the police stun gun, you had to fire it, and the 2 electrodes would hit the victim, and there's 2 wires connected to it, and then they pull the trigger. With the one I had, there were no electrodes. You actually had to touch the person, but this was 10,000 volts. 10,000 volts, and you say, well, isn't that a lot of voltage? Can't you kill the person? Well, voltage doesn't kill you. It's not voltage that kills you. Anybody know what kills you? What's fatal to you? Is it voltage, current, or resistance?
Current.
I just said it wasn't voltage, and it would be silly to say it's resistance. Current is what kills you. Milliamps is enough to stop your heart. So yeah, this is 10,000 volts. It's a very high voltage, but a low current. So it's enough current not to kill, well, in theory, it's not supposed to kill you. It's just supposed to incapacitate you, and they work pretty well. But that's not the point I'm making. The point I'm making, when you take the back off the one that I had, there's a little bitty square 9-volt battery in there. How you go from 9 volts DC to 10,000 volts? You do this. There's a circuit in there, and I can tell you it's real easy. It's a 555 timer. And what that does is it changes the current. You can make, once you take digital 1 or 2, you'll be able to use this. You'll know it in your sleep. But with that circuit, you can have a varying current like this. And basically, it's an electronic switch that you can turn off and on, but you have control over the frequency of this. So basically, you're controlling the IDT. And if you make the frequency really, really high, you're making the IDT really, really high, which means the voltage across the coil is really, really high. In theory, you can go from a 9-volt battery to 1,000,000 volts if you want to. It all works the same way, based on this equation right here, that differential equation that I talked about, that I erased. V induced is equal to L dIdt. Now I got off on the tangent. I didn't mean to do that because I actually wanted to get in here and work these problems. So I got about a little less than 10 minutes. Let me calm down, because you know when it's physics, I get excited. I get really excited because you can use this stuff, and you can make stun guns and rail guns, and I mean the little cute labs that we do on the boards. Those are good, but I want to make a stun gun. I want to make something big, and this stuff is fun. So let's go back to the video, and I want you to make a couple observations, and then we'll end it. And your exam is going to open up at 2 o'clock. I have it set to open up at 2 o'clock. So you'll need this information for the exam. So here's what you'll need. Inductors in series and inductors in parallel. Let's talk about that. It's really, really simple, because unlike capacitors, inductors act just like resistors. Now, what do I mean by that? Well, resistors in series, to find the total resistance, you just add them up. Inductors in series, to find the total inductance, you just add them up. Resistors in parallel, to find the total resistance, you use one of those parallel formulas. You can use the 1/R rule, the product over the sum rule. Well, inductors work the same way. Inductors in parallel work just like resistors in parallel. All you got to do if you have inductors in parallel is take the formula for any of your parallel resistor formulas and change the R's to L, and then you're good to go. So those are really, really easy. So I'm not going to spend a lot of time, because I don't want to run out of time, but I'm not going to spend a lot of time talking about the time constant. The time constant for a capacitor is R times C. Well, the time constant for an inductor is L over R. And we know at t equals 0, a capacitor acts like a short circuit. Well, everything that's true for a capacitor, the opposite is true for an inductor, which is interesting. Everything that's true for a capacitor, the opposite is true for an inductor. Now, what do I mean by that? Well, look at this. At t equals 0, a capacitor acts like a short. Well, at t equals 0, an inductor acts like an open. And then at t, when it's at 5 time constants, now remember, 5 tau is not RC. If we're talking about an inductor, tau is L over R. It's this one. But when that inductor is fully, I won't say charged, but when the magnetic field is fully inflated, it's not moving anymore, the capacitor acts like a short. So at t equals 0, a capacitor is an open. I keep saying capacitor. At t equals 0, an inductor acts like an open. And at 5 tau, the capacitor becomes a short. Exactly the opposite from capacitors. And then, just like with capacitors, if you're between T0 and steady state, then you have transient equations that we're not going to talk about, but they are in your book if you want to look or dig more into this. Now, I mentioned to you I was going to talk about why is it that I didn't spend as much time on inductors as I do capacitors. And let me briefly explain that. Then I want to quickly do those practice problems. Guys, if you think about it, electronics is getting smaller and smaller and smaller. And so if you look at the printed circuit board on your cell phone, it's tiny. I'm making it big here, but it's really tiny. And if they're putting surface mount resistors, they're putting capacitors, they're putting all that stuff in a smaller and smaller area. If you have an inductor here with a varying magnetic field, and you have other devices, you basically have Faraday's law going on. If I have an inductor and a capacitor real close to each other, and that inductor has a varying magnetic field, if that varying magnetic field goes across the lead of a resistor or the lead of a capacitor, it can actually induce, by Faraday's law, it can induce a voltage in a resistor or capacitor that's nearby. So engineers, when they can get away from using inductors, since they have varying magnetic fields that can cause unwanted voltages and currents that appear in the circuit, when you have an unwanted voltage or current in the circuit, one that's not supposed to be there, one that's there because of inductance, we call that noise. And that can cause problems in the electrical system. So you don't have that with capacitors. So often engineers will use capacitors in place of inductors because it eliminates the potential possibility of noise. Now let's go to the document, and there are 3 problems at the end. And we got about 4 minutes left. I'm gonna give you about maybe 2 or 3 of those minutes to calculate. We may go over, so if you guys got to go to another class, make sure you go back and watch the recording before you do the exam, because you'll need this information for part of your final exam. So make sure you look at these calculations before you do your exam, and then you should be in good shape. But go ahead and get a sheet of paper, do problem number 1, 2, and 3. I'll give you about 2 minutes to do it, and then we'll quickly go through it, and that'll be it for the semester. So I'll be quiet now. Okay, guys, let's go through this because we're out of time. I want to go through it just so you have it. Let's do number 2 and 3 because they're the quickest. Let me actually draw it so you can see what the symbol looks like. So when you draw an inductor, all you do is draw a coil. So we got 3 inductors in series. L1, L2, and L3, and they are 20, 40, and 60. The unit for inductance is a Henry. We use a capital H. These are, looks like these are, millihenries. 20 millihenries, 40 millihenries, 60 millihenries. So I want to find LT. So how do I find LT? Well, inductors in series act like resistors in series. You just add them up. So if I add up 20 plus 40, that's 60, plus 60, this would be 120 millihenries, 120 millihenries. Can you open the door, Riley? 120 millihenries. And then the next one is, we have 3. Are you dropping something off?
Yes,
Or,
sir.
okay, just put it on the table.
Do you have a stepper on top?
Yeah, there you go. I think there's something there. And just put it on the table over there. Thank you. So if you have, let's see, we have 3 inductors in there now. Same one in parallel, but this says assume no mutual induction. And what that means is that this inductor can actually induce a voltage on another inductor because it has a very magnetic field that can interact with each other. So they're saying that's not the case. Thank you. And since that's not the case, then we can go ahead and apply the rule that inductors in parallel act like resistors in parallel. So if I had 3 resistors in parallel, how would I find the total resistance? Well, you just say 1 over R T is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Well, if I have inductors in parallel, I would draw, of course, the inductors in parallel, but you just change all your R's to L's. This will be LT, this will be L1, L2, and finally L3. So I don't know if somebody did the math, but if you do the math, use a reciprocal key. This is 1 over 20 plus 1 over 40 plus 1 over 60 will be 1 over LT. And remember, these are already in millihenries, so I don't have to actually put them in millihenries. Does anybody have a calculator handy and tell me what you get for LT when you do the calculation? What's the total inductance? Well, you guys, you didn't see what I was writing because I didn't have my camera on. So here's what I wrote. I don't know if you guys can switch off of that. You know you can switch off of it. But you have 1 over LT is 1 over L1 plus 1 over L2 plus 1 over L3. So I put my 20 to 40 to 60 in there. What do you get when you do the math for LT? 400. How much? 400.
I came up with 10.
Okay, you got 10 millihenries. Anybody else get 10? I mean, it makes sense because, you know, if I have resistors in parallel, the total resistance has to be less than the smallest resistor. So that would be true for the inductance in parallel. The total inductance has to be less than the smallest, and the smallest is 20. Does anybody else get 10? Okay, well, I don't know if people are still working. I'm going to assume that that's the right
I also
answer.
got
Okay, we got somebody to second it. And then the very last one, let me go back to the sheet, and I want to do that last one. I don't know if I asked this on the final exam or not, but just in case I do, I want to go back to it. So in that very last sheet, if you look at problem number 1, it says calculate the inductance of a coil that induces 100 volts when its current changes by 5 milliamps in 10 microseconds. So go ahead and write out the equation. Make your list of what's known and unknown and what you're looking for. And then write the equation that you're going to use to solve. And then we'll compare our notes. So we have a calculate the inductance of a coil that induces 100 volts And it says the coil has, it doesn't really tell us the number of turns, so I guess we don't need that. So we know the coil is 100 volts. We want to know the inductance, which is L, and they give us the change in. They give us a change in current. All right, let me show you what I have because we're out of time. So here's what I have from the problem. I made a list of what they gave us and what we're looking for. They told us that the induced voltage is 100 volts. They told us that the time rate of change of current is 5 milliamps every 10 microseconds. Now again, if you don't want to write it that way, just write it as delta I over delta T. Either way, I don't care. But clearly, you can see what you're going to do. You're going to use this equation right here. So let me write it out. V induced, or VL, is going to equal L times di dt. So basically, we're solving this for L. So if you let this thing, if you let di dt be x, then you can replace this with x. And then it makes it look a little simpler. So we're looking for L. If I had this equation, I was looking for L, and I would just divide. L would just be VL over x, but of course x is equal to di dt. So it's going to be over di dt. Now you got to be careful when you put your numbers in. So when you put your numbers in, for VL you're going to have 100 volts. So you do have 100 divided by, but when you put di dt in, you want to put this in either in scientific notation or as a decimal. Do not take 5 and divide it by 10. That won't work. What you want to do is take 5 times 10 to the minus third amps and divide it by 10 times 10 to the minus 6 seconds. You want to do it that way in your calculator. And you got to use your parentheses. Now, does anybody have an answer? I may have to pull my calculator out, compare. So you gotta use 2 sets of parentheses, but let me go ahead and do it on my calculator. So I have 100 divided by paren. I got 5 times 10 to the minus third divided by 10 times 10 to the minus 6, close paren, equal, and what I got is 200 milliamps. I'll put it in there right. Or I'm sorry, 200, 0.2. Uh-oh. Did you guys, what happened? Oh. I think I threw my calculator down on the line. I thought I lost you guys.
I'm still here.
Okay. So I got, when I did this, if I did my math right, I got 0.2 Henrys. Does anybody else get that number? Let me do it one more time to make sure.
I also got that number.
Okay. Well, we're going to go with that. It'll be 0.2 Henrys or 200 millihenries. Okay, so I went through that kind of quickly, but you can always go back and watch the video. Anybody have any questions or comments on anything I talked about today? All right, well, guys, that ends. You guys have made it well, you still got to take the final, but I think you'll find the final to be pretty simple. So you guys, for the most part, you made it through circuits 1, and now you got to gear up and be ready for circuits 2. So keep in touch, and if anybody has any questions, please don't throw anything away until after you get your grade on Blackboard and you agree with that grade. Because if something doesn't jive up, you got to be able to prove to me, hey, I turned that in, or you put the wrong grade, whatever. Keep everything. I would keep your 3-ring binder, because if you end up taking me for AC, we're going to pick up where we left off. If you take Dr. Whaley or somebody else for AC, that's still good information to have. So keep that. And guys, have a great rest of the day. Have a great summer, and hopefully I'll see you guys around campus, and please keep in touch.
When will final grades be in?
They will be in on Wednesday, and they should be available to you on Thursday.
All righty.
See you later.
Have a good one. Thank you.
Later.
Thank you. Bye-bye.